I mean, it's fun, and pytorch's symbol is a flame because of torch. But let's get into it. So naturally, if you've come to this course, you might have already researched what is deep learning, but we're going to cover it quite briefly, and just in the sense of how much you need to know for this course, because we're going to be more focused on, rather than just definitions, we're going to be focused on getting practical and seeing things happen. So if we define what machine learning is, because as we'll see in a second, deep learning is a subset of machine learning. Machine learning is turning things, data, which can be almost anything, images, text, tables of numbers, video, audio files, almost anything can be classified as data, into numbers. So computers love numbers, and then finding patterns in those numbers. Now, how do we find those patterns? Well, the computer does this part, specifically a machine learning algorithm or a deep learning algorithm, the things that we're going to be building in this course. How? Code and math. Now, this course is code focused. I want to stress that before you get into it. We're focused on writing code. Now, behind the scenes, that code is going to trigger some math to find patterns in those numbers. If you would like to deep dive into the math behind the code, I'm going to be linking extra resources for that. However, we're going to be getting hands-on and writing lots of code to do lots of this. And so if we keep going to break things down a little bit more, machine learning versus deep learning. If we have this giant bubble here of artificial intelligence, you might have seen something similar like this on the internet. I've just copied that and put it into pretty colors for this course. So you've got this overarching big bubble of the topic of artificial intelligence, which you could define as, again, almost anything you want. Then typically there's a subset within artificial intelligence, which is known as machine learning, which is quite a broad topic. And then within machine learning, you have another topic called deep learning. And so that's what we're going to be focused on, working with PyTorch, writing deep learning code. But again, you could use PyTorch for a lot of different machine learning things. And truth be told, I kind of use these two terms interchangeably. Yes, ML is the broader topic and deep learning is a bit more nuanced. But again, if you want to form your own definitions of these, I'd highly encourage you to do so. This course is more focused on, rather than defining what things are, is seeing how they work. So this is what we're focused on doing. Just to break things down, if you're familiar with the fundamentals of machine learning, you probably understand this paradigm, but we're going to just rehash on it anyway. So if we consider traditional programming, let's say you'd like to write a computer program that's enabled to, or has the ability to reproduce your grandmother's favorite or famous roast chicken dish. And so we might have some inputs here, which are some beautiful vegetables, a chicken that you've raised on the farm. You might write down some rules. This could be your program. Cut the vegetables, season the chicken, preheat the oven, cook the chicken for 30 minutes and add vegetables. Now, it might not be this simple, or it might actually be, because your Sicilian grandmother is a great cook, so she's put things into an art now and can just do it step by step. And then those inputs combined with those rules makes this beautiful roast chicken dish. So that's traditional programming. Now, a machine learning algorithm typically takes some inputs and some desired outputs and then figures out the rules, so the patterns between the inputs and the outputs. So where in traditional programming we had to hand write all of these rules, the ideal machine learning algorithm will figure out this bridge between our inputs and our idealized output. Now, in the machine learning sense, this is typically described as supervised learning, because you will have some kind of input with some kind of output, also known as features and also known as labels. And the machine learning algorithm's job is to figure out the relationships between the inputs or the features and the outputs or the label. So if we wanted to write a machine learning algorithm to figure out our Sicilian grandmother's famous roast chicken dish, we would probably gather a bunch of inputs of ingredients such as these delicious vegetables and chicken, and then have a whole bunch of outputs of the finished product and see if our algorithm can figure out what we should do to go from these inputs to output. So that's almost enough to cover of the difference between traditional programming and machine learning as far as definitions go. We're going to get hands-on in coding these sort of algorithms throughout the course. For now, let's go to the next video and ask the question, why use machine learning or deep learning? And actually, before we get there, I'd like you to think about that. So going back to what we just saw, the paradigm between traditional programming and machine learning, why would you want to use machine learning algorithms rather than traditional programming? So if you had to write all these rules, could that get cumbersome? So have a think about it, and we'll cover it in the next video. Welcome back. So in the last video, we covered briefly the difference between traditional programming and machine learning. And again, I don't want to spend too much time on definitions. I'd rather you see this in practice. And I left you with the question, why would you want to use machine learning or deep learning? Well, let's think of a good reason. Why not? I mean, if we had to write all those handwritten rules to reproduce our Sicilian grandmother's roast chicken dish all the time, that would be quite cumbersome, right? Well, let's draw a line on that. Why not? What's a better reason? And kind of what we just said, right? For a complex problem, can you think of all the rules? So let's imagine we're trying to build a self-driving car. Now, if you've learned to drive, you've probably done so in maybe 20 hours, 100 hours. But now I'll give you a task of writing down every single rule about driving. How do you back out of your driveway? How do you turn left and go down the street? How do you park, a reverse park? How do you stop at an intersection? How do you know how fast to go somewhere? So we just listed half a dozen rules, but you could probably go a fair few more. You might get into the thousands. And so for a complex problem such as driving, can you think of all the rules? Well, probably not. So that's where machine learning and deep learning come in to help. And so this is a beautiful comment I'd like to share with you on one of my YouTube videos. It is my 2020 machine learning roadmap. And this is from Yashui. I'm probably going to mispronounce this if I even try to. But Yashui says, I think you can use ML. So ML is machine learning. I'm going to use that a lot throughout the course, by the way. ML is machine learning, just so you know. For literally anything, as long as you can convert it into numbers. That's what we said before. Machine learning is turning something into computer readable numbers. and then programming it to find patterns, except with a machine learning algorithm, typically we write the algorithm and it finds the patterns, not us. And so literally it could be anything, any input or output from the universe. That's pretty darn cool about machine learning, right? But should you always use it just because it could be used for anything? Well, I'd like to also introduce you to Google's #1 rule of machine learning. Now, if you can build a simple rule-based system such as the step of 5 rules that we had to map the ingredients to our Sicilian grandmother's roast chicken dish, if you can write just 5 steps to do that, that's going to work every time, well, you should probably do that. So if you can build a simple rule-based system that doesn't require machine learning, do that. And of course, maybe it's not so very simple. Learning handbook. Now, I'm going to highly recommend you read through that, but we're not going to go through that in this video. So check that out. You can Google that. Otherwise, the links will be where you get links. So just keep that in mind. Although machine learning is very powerful and very fun and very excited, it doesn't mean that you should always use it. I know this is quite the thing to be saying at the start of a deep learning and machine learning course, but I just want you to keep in mind, simple rule-based systems are still good. Machine learning isn't a solve-all for everything. Now let's have a look at what deep learning is good for. But I'm going to leave you on a cliffhanger because we're going to check this out in the next video. See you soon. In the last video, we familiarized ourselves with Google's #1 rule of machine learning, which is basically, if you don't need it, don't use it. And with that in mind, what should we actually be looking to use machine learning or deep learning for? Well, problems with long lists of rules. So when the traditional approach fails, so remember, the traditional approach is you have some sort of data input, you write a list of rules for that data to be manipulated in some way, shape, or form, and then you have the outputs that you know. But if you have a long, long list of rules, like the rules of driving a car, which could be hundreds, could be thousands, could be millions, who knows? That's where machine learning and deep learning may help, and it kind of is at the moment. In the world of self-driving cars, machine learning and deep learning are the state-of-the-art approach. Continually changing environments. So one of the benefits of deep learning is that it can keep learning if it needs to. And so it can adapt and learn to new scenarios. So if you update the data that your model was trained on, it can adjust to new different kinds of data in the future. So similarly to if you are driving a car, you might know your own neighborhood very well. But then when you go to somewhere you haven't been before, sure, you can draw on the foundations of what you know, but you're going to have to adapt. How fast should you go? Where should you stop? Where should you park? These kinds of things. So with problems with long list of rules or continually changing environments, or if you had a large data set. And so this is where deep learning is flourishing in the world of technology. So let's give an example. One of my favorites is the Food 101 dataset, which you can search for online, which is images of 101 different kinds of foods. Now, we briefly looked at what a rule list might look like for cooking your grandmother's famous Sicilian roast chicken dish. But can you imagine if you wanted to build an app that could take photos of different food, how long your list of rules would be to differentiate 101 different foods? It'd be so long. You need rule sets for every single one. Let's just take one food, for example. How do you write a program to tell what a banana looks like? I mean, you'd have to code what a banana looks like, but not only a banana, what everything that isn't a banana looks like. So keep this in mind. What deep learning is good for? Problems with long lists of rules, continually changing environments, or discovering insights within large collections of data. Now, what deep learning is not good for, and I'm going to write typically here because, again, this is problem specific. Deep learning is quite powerful these days and things might change in the future. So keep an open mind. If there's anything about this course, it's not for me to tell you exactly what's what. It's for me to spark a curiosity into you to figure out what's what. Or even better yet, what's not what. So when you need explainability, as we'll see, the patterns learned by a deep learning model, which is lots of numbers, called weights and biases, we'll have a look at that later on, are typically uninterpretable by a human. So some of the times, deep learning models can have 1 million, 10 million, 100 million, a billion. Some models are getting into the trillions of parameters. When I say parameters, I mean numbers or patterns in data. Remember, machine learning is turning things into numbers and then writing a machine learning model to find patterns in those numbers. So sometimes those patterns themselves can be lists of numbers that are in the millions. And so can you imagine looking at a list of numbers that has 1 million different things going on? That's going to be quite hard. I find it hard to understand 3 or 4 numbers, let alone 1 million. And when the traditional approach is a better option, again, this is Google's rule #1 of machine learning. If you can do what you need to do with a simple rule-based system, well, maybe you don't need to use machine learning or deep learning. Again, I'm going to use the deep learning, machine learning terms interchangeably. I'm not too concerned with definitions. You can form your own definitions, but just so you know, from my perspective, ML and deep learning are quite similar. When errors are unacceptable. So since the outputs of a deep learning model aren't always predictable, we'll see that deep learning models are probabilistic. That means when they predict something, they're making a probabilistic bet on it. Whereas in a rule-based system, you kind of know what the outputs are going to be every single time. So if you can't have errors based on probabilistic errors, well, then you probably shouldn't use deep learning and you'd like to go back to a simple rule-based system. And then finally, when you don't have much data. So deep learning models usually require a fairly large amount of data to produce great results. However, there's a caveat here. You know, at the start I said typically, we're going to see some techniques of how to get great results without huge amounts of data. And again, I wrote typically here because there are techniques. You can just research deep learning explainability. You're going to find a whole bunch of stuff. You can look up examples of when machine learning versus deep learning. And then when errors are unacceptable, again, there are ways to make your model reproducible. So it predicts, you know what's going to come out. So we do a lot of testing to verify this as well. And so what's next? We've got machine learning versus deep learning, and we're going to have a look at some different problem spaces in a second, and mainly breaking down in terms of what kind of data you have. Not going to do this now, prevent this video from getting too long. We'll cover all these colorful, beautiful pictures in the next video. Welcome back. So in the last video, we covered a few things of what deep learning is good for and what deep learning is typically not good for. So let's dive into a little more of a comparison of machine learning versus deep learning. Again, I'm going to be using these terms quite interchangeably, but there are some specific things that typically you want traditional style of machine learning techniques versus deep learning. However, this is constantly changing. So again, I'm not talking in absolutes here. I'm more just talking in general, and I'll leave it to you to use your own curiosity to research the specific differences between these two. But typically, for machine learning, like the traditional style of algorithms, although they are still machine learning algorithms, which is kind of a little bit confusing where deep learning and machine learning differ, is you want to use traditional machine learning algorithms on structured data. So if you have tables of numbers, this is what I mean by structured. Rows and columns, structured data. And possibly one of the best algorithms for this type of data is a gradient boosted machine, such as XGBoost. This is an algorithm that you'll see in a lot of data science competitions and also used in production settings. When I say production settings, I mean applications that you may interact with on the internet or use on a day-to-day. So that's production. XGBoost is typically the favorite algorithm for these kinds of situations. So again, if you have structured data, you might look into XGBoost rather than building a deep learning algorithm. But again, the rules aren't set in stone. That's where deep learning and machine learning is kind of an art, kind of a science, is that sometimes XGBoost is the best for structured data, but there might be exceptions to the rule. But for deep learning, it is typically better for unstructured data. And what I mean by that is data that's kind of all over the place. It's not in your nice standardized rows and columns. So say you had natural language, such as this tweet by this person whose name is quite similar to mine and has the same Twitter account as me. Oh, maybe I wrote that. How do I learn machine learning? What you need to hear, learn Python, learn math, stats, probability, software engineering, build. What you need to do, Google it, go down the rabbit hole, resurface in 6 to 9 months and reassess. I like that. Or if you had a whole bunch of text, such as the definition for deep learning on Wikipedia. Again, this is the reason why I'm not covering as many definitions in this course, is because look how simple you can look these things up. Wikipedia is going to be able to define deep learning far better than what I can. I'm more focused on just getting involved in working hands-on with this stuff than defining what it is. And then we have images. If we wanted to build a burger, take a photo app thing, you would work with image data, which doesn't really have much of a structure, although we'll see that there are ways for deep learning that we can turn this kind of data to have some sort of structure through the beauty of a tensor. And then we might have audio files, such as if you were talking to your voice assistant. I'm not going to say one because a whole bunch of my devices might go crazy if I say the name of my voice assistant, which rhymes with, I'm not even going to say that out loud. And so typically for unstructured data, you'll want to use a neural network of some kind. So structured data, gradient boosted machine, or a random forest, or a tree-based algorithm, such as XGBoost, and unstructured data, neural networks. So let's keep going. Let's have a look at some of the common algorithms that you might use for structured data, machine learning, versus unstructured data, deep learning. So random forest is one of my favorites, gradient boosted models, naive Bayes, nearest neighbor, support vector machine, SVM, and then many more. But since the advent of deep learning, these are often referred to as shallow algorithms. So deep learning, why is it called deep learning? Gradient for structured data, machine learning, versus unstructured data, deep learning. So random forest is one of my favorites, gradient boosted models, naive Bayes, nearest neighbor, support vector machine, SVM, and then many more. But since the advent of deep learning, these are often referred to as shallow algorithms. So deep learning, why is it called deep learning? Well, as we'll see, is that it can have many different layers of algorithm. You might have an input layer, 100 layers in the middle, and then an output layer. But we'll get hands-on with this later on. And so common algorithms for deep learning are neural networks, fully connected neural network, convolutional neural network, recurrent neural network, transformers have taken over the past couple of years, and of course, many more. And the beautiful thing about deep learning and neural networks is there's almost as many problems that it can be applied to is as many different ways that you can construct them. So this is why I'm putting all these dot points on the page, and I can understand if you haven't had much experience with machine learning or deep learning, this can be a whole bunch of information overload. But good news is, what we're going to be focused on building with PyTorch is neural networks, fully connected neural networks, and convolutional neural networks, the foundation of deep learning. But the excellent thing is, the exciting thing is that if we learn these foundational building blocks, we can get into these other styles of things here. And again, part art, part science of machine learning and deep learning is depending on how you represent your problem, depending on what your problem is. Many of the algorithms here and here can be used for both. So I know I've just kind of bedazzled you in saying that, oh, well, you kind of use these ones for deep learning, you kind of use these ones for machine learning, but depending on what your problem is, you can also use both. So that's a little bit of confusion to machine learning, but that's the fun part about it too, is use your curiosity to figure out what's best for whatever you're working on. And with all this talk about neural networks, how about in the next video, we cover what are neural networks? Now, I'd like you to Google this before we watch the next video, because there's going to be hundreds of definitions of what they are, and I'd like you to start forming your own definition of what a neural network is. I'll see you in the next video. Welcome back. In the last video, I left you with a cliffhanger of a question. What are neural networks? And I gave you the challenge of Googling that, but you might have already done that by the time you've got here. Let's just do that together. If I type in what are neural networks? I've already done this. What are neural networks? Explain neural networks, neural network definition. There are hundreds of definitions of things like this online. Neural network in 5 minutes. 3 Blue 1 Brown. I'd highly recommend that channel series on neural networks. That's going to be in the extra curriculum. StatQuest is also amazing. So there's hundreds of different definitions on here, and you can read 10 of them, 5 of them, 3 of them, make your own definition. But for the sake of this course, here's how I'm going to define neural networks. So we have some data of whatever it is. We might have images of food, we might have tweets or natural language, and we might have speech. So these are some examples of inputs for unstructured data because they're not rows and columns. So these are the input data that we have. And then, how do we use them with a neural network? Well, before data can be used in a neural network, it needs to be turned into numbers because humans, we like looking at images of ramen and spaghetti. We know that that's ramen, we know that that's spaghetti after we've seen it 1 or 2 times. And we like reading good tweets, and we like listening to amazing music or hearing our friend talk on the phone in audio file. However, before a computer understands what's going on in these inputs, it needs to turn them into numbers. So this is what I call a numerical encoding or a representation. And this numerical encoding, these square brackets indicate that it's part of a matrix or a tensor, which we're going to get very hands-on with throughout this course. So we have our inputs, we've turned it into numbers, and then we pass it through a neural network. And now this is a graphic for a neural network. However, the graphics for neural networks, as we'll see, can get quite involved, but they all represent the same fundamentals. So if we go to this one, for example, we have an input layer, then we have multiple hidden layers. However you define this, you can design these in how you want. And then we have an output layer. So our inputs will go in, some kind of data. The hidden layers will perform mathematical operations on the input, so the numbers, and then we'll have an output. Oh, there's 3 Blue 1 Brown neural networks from the ground up. Great video. Highly recommend you check that out. But then if we come back to this, so we've got our inputs, we've turned it into numbers, and we've got our neural networks that we put the input in. This is typically the input layer, hidden layer. This can be as many different layers as you want, as many different, each of these little dots is called a node. There's a lot of information here, but we're going to get hands-on with seeing what this looks like. And then we have some kind of output. Now, which neural network should you use? Well, you can choose the appropriate neural network for your problem, which could involve you hand coding each one of these steps, or you could find one that has worked on problems similar to your own, such as for images, you might use a CNN, which is a convolutional neural network. For natural language, you might use a transformer. For speech, you might also use a transformer. But fundamentally, they all follow the same principle of inputs, manipulation, outputs. And so the neural network will learn a representation on its own. We won't define what it learns. So it's going to manipulate these patterns in some way, shape, or form. And when I say learns representation, I'm going to also refer to it as learns patterns in the data. A lot of people refer to it as features. A feature may be the fact that the word do comes after how, usually, in across a whole bunch of different languages. A feature can be almost anything you want. And again, we don't define this. The neural network learns these representations, patterns, features, also called weights, on its own. And then where do we go from there? Well, we've got some sort of numbers, numerical encoding, turned our data into numbers. Our neural network has learned a representation that it thinks best represents the patterns in our data. And then it outputs those representation outputs, which we can use. And often you'll hear this referred to as features or weight matrix or weight tensor. Learned representation is also another common one. There's a lot of different terms for these things. And then it will output. We can convert these outputs into human understandable outputs. So if we were to look at these could be, again, I said representations or patterns that a neural network learns can be millions of numbers. This is only 9. So imagine if these were millions of different numbers. I can barely understand the 9 numbers that is going on here. So we need a way to convert these into human understandable terms. So for this example, we might have some input data, which are images of food. And then we want our neural network to learn the representations between an image of ramen and an image of spaghetti. And then eventually we'll take those patterns that it's learned and we'll convert them into whether it thinks that this is an image of ramen or spaghetti. Or in the case of this tweet, is this a tweet for a natural disaster or not a natural disaster? So our neural network has, well, we've written code to turn this into numbers, pass it through our neural network. Our neural network has learned some kind of patterns, and then we ideally want it to represent this tweet as not a disaster. And then we can write code to do each of these steps here. And the same thing for these inputs going as speech, turning into something that you might say to your smart speaker, which I'm not going to say because a whole bunch of my devices might go off. And so let's cover the anatomy of neural networks. We've hinted at this a little bit already, but this is like neural network anatomy 101. Again, this is highly customizable what this thing actually is. We're going to see it in PyTorch code later on, but the data goes into the input layer. And in this case, the number of units / neurons / nodes is 2. Hidden layers, you can have, I put a S here because you can have one hidden layer, or the deep in deep learning comes from having lots of layers. So this is only showing 4 layers. You might have, well, this is 3 layers as well. Might be very deep neural networks such as ResNet 152. This is 152 different layers. So again, you can, oh, this is 34 because this is only ResNet 34, but ResNet 152 has 152 different layers. So that's a common computer vision or a popular computer vision algorithm, by the way. Lots of terms we're throwing out here, but with time, you'll start to become familiar with them. So hidden layers can be almost as many as you want. We've only got pictured 1 here, and in this case, there's 3 hidden units / neurons, and then we have an output layer. So the outputs learned representation or prediction probabilities from here, depending on how we set it up, which, again, we will see what these are later on. And in this case, it has 1 hidden unit. So 2 input, 3, 1 output. You can customize the number of these. You can customize how many layers there are. You can customize what goes into here. You can customize what goes out of there. So Now, if we talk about the overall architecture, which is describing all of the layers combined. So that's when you hear neural network architecture, it talks about the input, the hidden layers, which may be more than one, and the output layer. So that's a terminology for overall architecture. Now, I say patterns is an arbitrary term. You can hear embedding. Embedding might come from hidden layers, weights, feature representation, feature vectors, all referring to similar things. So again, how do we turn our data into some numerical form, build a neural network to figure out patterns to output some desired output that we want? And now, to get more technical, each layer is usually a combination of linear, so straight lines, and non-linear, non-straight functions. So what I mean by that is a linear function is a straight line, a non-linear function is a non-straight line. If I ask you to draw whatever you want with unlimited straight lines and not straight lines, so you can use straight lines or curved lines, what kind of patterns could you draw? At a fundamental level, that is basically what a neural network is doing. It's using a combination of linear, straight lines, and not straight lines to draw patterns in our data. We'll see what this looks like later on. Now, for the next video, let's dive in briefly to different kinds of learning. So we've looked at what a neural network is, the overall algorithm, but there are also different paradigms of how a neural network learns. I'll see you in the next video. Welcome back. We've discussed a brief overview of an anatomy of what a neural network is, but let's now discuss some learning paradigms. So the first one is supervised learning, and then we have unsupervised and self-supervised learning, and transfer learning. Now, supervised learning is when you have data and labels, such as in the example we gave at the start, which was how you would build a neural network or a machine learning algorithm to figure out the rules to cook your Sicilian grandmother's famous roast chicken dish. So in the case of supervised learning, you'd have a lot of data, so inputs, such as raw ingredients as vegetables and chicken, and a lot of examples of what that inputs should ideally look like. Or in the case of discerning photos between a cat and a dog, you might have 1,000 photos of a cat and 1,000 photos of a dog that you know which photos are cat and which photos are dog, and you pass those photos to a machine learning algorithm to discern. So in that case, you have data, the photos, and the labels, aka cat and dog, for each of those photos. So that's supervised learning, data and labels. Unsupervised and self-supervised learning is you just have the data itself. You don't have any labels. So in the case of cat and dog photos, you only have the photos. You don't have the labels of cat and dog. So in the case of self-supervised learning, you could get a machine learning algorithm to learn an inherent representation of what, and when I say representation, I mean patterns and numbers, I mean weights, I mean features, a whole bunch of different names describing the same thing. You could get a self-supervised learning algorithm to figure out the fundamental patterns between a dog and a cat image, but it wouldn't necessarily know the difference between the two. That's where you could come in later and go, show me the patterns you've learned. And it might show you the patterns, and you could go, okay, the patterns that look like this are dog, and the patterns that look like that are cat. So self-supervised and unsupervised learning learns solely on the data itself. And then finally, transfer learning is a very, very important paradigm in deep learning. It's taking the patterns that one model has learned of a data set and transferring it to another model, such in the case of if we were trying to build a supervised learning algorithm for discerning between cat and dog photos, we might start with a model that has already learned patterns and images and transfer those foundational patterns to our own model so that our model gets a head start. Transfer learning is a very, very powerful technique. But as for this course, we're going to be writing code to focus on these two, supervised learning and transfer learning, which are two of the most common paradigms or common types of learning in machine learning and deep learning. However, this style of code, though, can be adapted across different learning paradigms. Now, I just want to let you know there is one that I haven't mentioned here, which is kind of in its own bucket, and that is reinforcement learning. So I'll leave this as an extension if you wanted to look it up. But essentially, this is a good one. It's a good photo, actually, so shout out to Katie Nuggets. The whole idea of reinforcement learning is that you have some kind of environment and an agent that does actions in that environment, and you give rewards and observations back to that agent. So say, for example, you wanted to teach your dog to urinate outside. Well, you would reward its actions of urinating outside and possibly not reward its actions of urinating all over your couch. So reinforcement learning is, again, it's kind of in its own paradigm. This picture has a good explanation between unsupervised learning, supervised learning to separate two different things, and then reinforcement learning is kind of like that. But again, I will let you research the different learning paradigms a little bit more in your own time. As I said, we're going to be focused on writing code to do supervised learning and transfer learning, specifically PyTorch code. Now, with that covered, let's get a few examples of what is deep learning actually used for. And before we get into the next video, I'm going to issue you a challenge to search this question yourself and come up with some of your own ideas for what deep learning is currently used for. So give that a shot, and I'll see you in the next video. How'd you go? Did you do some research? Did you find out what deep learning is actually used for? I bet you found a treasure trail of things. And hey, I mean, if you're reading this course, course, chances are that you probably already know some use cases for deep learning. You're like, Daniel, hurry up and get to the code. Well, we're going to get there, don't you worry. But let's have a look at some things that deep learning can be used for. But before, I just want to remind you of this comment. This is from Yashaswi on the 2020 Machine Learning Roadmap video. I think you can use ML, and remember ML is machine learning, and remember deep learning is a part of ML, for literally anything, as long as you can convert it into numbers and program it to find patterns. Literally, it could be anything, any input or output from the universe. So that's a beautiful thing about machine learning, is that if you can encode something into numbers, chances are you can build a machine learning algorithm to find patterns in those numbers. Will it work? Well, again, that's the reason machine learning and deep learning is part art, part science. A scientist would love to know that their experiments would work, but an artist is kind of excited about the fact that, I don't know, this might work, it might not. And so that's something to keep in mind. Along with the rule number one of machine learning is if you don't need it, you don't use it. But if you do use it, it can be used for almost anything. And let's get a little bit specific and find out some deep learning use cases. And I've put some up there for a reason because there are lots. These are just some that I interact with in my day-to-day life, such as recommendation. We've got a programming video. We've got a programming podcast. We got some jiu-jitsu videos. We've got some RuneScape videos, a soundtrack from my favorite movie. Have you noticed, whenever you go to YouTube, you don't really search for things anymore? Well, sometimes you might, but the recommendation page is pretty darn good. That's all powered by deep learning. And in the last 10 years, have you noticed that translation has got pretty good too? Well, that's powered by deep learning as well. Now, I don't have much hands-on experience with this. I did use it when I was in Japan. I speak a very little amount of Japanese and an even smaller amount of Mandarin. But if I wanted to translate deep learning as epic to Spanish, it might come out as El aprendizaje profundo es épico. Now, all of the native Spanish speakers watching this video can laugh at me because that was a very Australian version of saying deep learning is epic in Spanish. But that's so cool. All of Google Translate is now powered by deep learning. And the beautiful thing, if I couldn't say it myself, I could click this speaker and it would say it for me. So that's speech recognition that's powered by deep learning. So if you were to ask your voice assistant who's the biggest big dog of them all, of course they're going to say you, which is what I've set up my voice assistant to say. That's part of speech recognition. And in computer vision, oh, look at this. You see this? Where is this photo from? This photo is from this person driving this car, did a hit and run on my car at the front of my house, my apartment building. My car was parked on the street. This car, the trailer came off, ran into the back of my car, basically destroyed it, and then they drove off. However, my next door neighbor's security camera picked up on this car. Now, I became a detective for a week, and I thought, if there was a computer vision algorithm built into that camera, it could have detected when the car hit. I mean, it took a lot of searching to find it. It turns out the car hit about 3:30 a.m. in the morning, so it was pitch black. And of course, we didn't get the license plate. So this person is out there somewhere in the world after doing a hit and run. So if you're watching this video, just remember, computer vision might catch you one day. So this is called object detection, where you would place a box around the area where the pixels most represent the object that you're looking for. So for computer vision, we could train an object detector to capture cars that drive past a certain camera. And then if someone does a hit and run on you, you could capture it. And then fingers crossed, it's not too dark that you can read the license plate and go, hey, excuse me, please, this person has hit my car and wrecked it. So that's a very close to home story of where computer vision could be used. And then finally, natural language processing. Have you noticed as well, your spam detector on your email inbox is pretty darn good? Well, some are powered by deep learning, some not. It's hard to tell these days what is powered by deep learning, what isn't. But natural language processing is the process of looking at natural language text, so unstructured text, so whatever you'd write in an email, in a story, in a Wikipedia document, and deciding or getting your algorithm to find patterns in that. So for this example, you would find that this email is not spam. This deep learning course is incredible. I can't wait to use what I've learned. Thank you so much. And by the way, that is my real email, so if you want to email me, you can. And then this is spam. Hey, Daniel, congratulations, you win a lot of money. Wow, I would really like that. A lot of money, but for some reason I don't think that this is real. So that would probably go to my spam inbox. Now, with that being said, if we wanted to put these problems in a little bit more of a classification, this is known as sequence to sequence because you put one sequence in and get one sequence out. Same as this, you have a sequence of audio waves and you get some text out. So sequence to sequence, sec to sec. This is classification / regression. In this case, the regression is predicting a number. That's what a regression problem is. You would predict the coordinates of where these box corners should be. So say this should be at however many pixels in from the X angle and however many pixels down from the Y angle. That's that corner. And then you would draw in between the corners, and then the classification part would go, hey, this is that car that did a hit and run on us. And in this case, this is classification. Classification is predicting whether something is one thing or another, or perhaps more than one thing or another in the class of multi-class classification. So this email is not spam, that's a class, and this email is spam. So that's also a class. So I think we've only got one direction to go now that we've sort of laid the foundation for the course, and that is, well, let's start talking about PyTorch. I'll see you in the next video. Well, let's now cover some of the foundations of PyTorch. But first, you might be asking, what is PyTorch? Well, of course, we could just go to our friend, the internet, and look up pytorch.org. This is the homepage for PyTorch. This course is not a replacement for everything on this homepage. This should be your ground truth for everything PyTorch. So you can get started. You've got a big ecosystem. You've got a way to set up on your local computer. You've got resources. You've got docs, PyTorch. You've got the GitHub. You've got search. You've got blog. Everything here. This website should be the place you're visiting most throughout this course. As we're writing PyTorch code, you're coming here, you're reading about it, you're checking things out, you're looking at examples. But for the sake of this course, let's break PyTorch down. Oh, there's a little flame animation I just forgot about. What is PyTorch? I didn't sync up the animations, that's all right. So, So PyTorch is the most popular research deep learning framework. An asterisk to that, I'll get to that in a second. It allows you to write fast deep learning code in Python. So if you know Python, it's a very user-friendly programming language, and PyTorch allows us to write state-of-the-art deep learning code accelerated by GPUs with Python. It enables you access to many pre-built deep learning models from Torch Hub, which is a website that has lots of, if you remember, I said transfer learning is a way that we can use other deep learning models to power our own. Torch Hub is a resource for that, same as torchvision.models. We'll be looking at this throughout the course. And it provides an ecosystem for the whole stack of machine learning, from pre-processing data, getting your data into tensors. What if you started with some images? How do you represent them as numbers? Then you can build models such as neural networks to model that data. Then you can even deploy your model in your application/cloud. Well, deploy your PyTorch model. Application/cloud will be depending on what sort of application/cloud that you're using, but generally it will run some kind of PyTorch model. And it was originally designed and used in-house by Facebook/Meta. I'm pretty sure Facebook have renamed themselves Meta now. But it is now open source and used by companies such as Tesla, Microsoft, and OpenAI. And when I say it is the most popular deep learning research framework, don't take my word for it. Let's have a look at paperswithcode.com/trends. If you're not sure what Papers with Code is, it is a website that tracks the latest and greatest machine learning papers and whether or not they have code. So we have some other languages here, other deep learning frameworks. PyTorch, TensorFlow, JAX is another one, MXNet, PaddlePaddle, the original Torch. So PyTorch is an evolution of Torch written in Python, CAF2, MindSpore. But if we look at this, when is this? Last date is December 2021. We have, oh, this is going to move every time I move it. No. So I'll highlight PyTorch at 58% there. So by far and large, the most popular research machine learning framework used to write the code for state-of-the-art machine learning algorithms. So this is browse state-of-the-art, paperswithcode.com, amazing website. We have semantic segmentation, image classification, object detection, image generation, computer vision, natural language processing, medical. I'll let you explore this. It's one of my favorite resources for staying up to date on the field. But as you see, out of the 65,000 papers with code that this website has tracked, 58% of them are implemented with PyTorch. How cool is that? And this is what we're learning. So let's jump into there. Why PyTorch? Well, other than the reasons that we just spoke about, it's a research favorite. This is highlighting. There we go. So there we go. I've highlighted it here. PyTorch, 58%, nearly 2,500 repos. If you're not sure what a repo is a place where you store all of your code online. And generally, if a paper gets published in machine learning, if it's fantastic research, it will come with code that you can access and use for your own applications or your own research. Again, why PyTorch? Well, this is a tweet from Francois Chalet, who's the author of Keras, which is another popular deep learning framework. But with tools like Colab, we're going to see what Colab is in a second, Keras and TensorFlow, I've added in here, and PyTorch, virtually anyone can solve in a day with no initial investment problems that would have required an engineering team working for a quarter and $20,000 in hardware in 2014. So this is just to highlight how good the space of deep learning and machine learning tooling has become. Colab, Keras, and TensorFlow are all fantastic, and now PyTorch is added to this list. If you want to check that out, there's Francois Chalet on Twitter. Very, very prominent voice in the machine learning field. Why PyTorch? If you want some more reasons, well, have a look at this. Look at all the places that are using PyTorch. It's just coming up everywhere. We've got Andre Karpathy here, who's the director of AI at Tesla. So if we go, we could search this, PyTorch at Tesla. We've got a YouTube talk there, Andre Karpathy, director of AI at Tesla. And so Tesla are using PyTorch for the computer vision models of autopilot. So if we go videos, or maybe images, does it come up there? Things like this, a car detecting what's going on in a scene. Of course, there'll be some other code for planning, but I'll let you research that. We come back here. OpenAI, which is one of the biggest open artificial intelligence research firms, open in the sense that they publish a lot of their research methodologies. However, recently there's been some debate about that. But if you go to openai.com, let's just say that they're one of the biggest AI research entities in the world, and they've standardized on PyTorch. So they've got a great blog, they've got great research, and now they've got OpenAI API, which is, you can use their API to access some of the models that they've trained, presumably with PyTorch, because this blog post from January 2020 says that OpenAI is now standardized across PyTorch. There's a repo called The Incredible PyTorch, which collects a whole bunch of different projects that are built on top of PyTorch. That's the beauty of PyTorch, is that you can build on top of it, you can build with it. AI for AG, for agriculture. PyTorch has been used. Let's have a look. PyTorch in agriculture. There we go. Agricultural robots use PyTorch. This is a Medium article. It's everywhere. So if we go down here, this is using object detection. Beautiful. Object detection to detect what kind of weeds should be sprayed with fertilizer. This is just one of many different things. So PyTorch on a big tractor like this, it can be used almost anywhere. And if we come back, PyTorch builds the future of AI and machine learning at Facebook. So Facebook, which is also Meta AI, a little bit confusing, even though it says Meta AI, it's on ai.facebook.com. That may change by the time you watch this. They use PyTorch in-house for all of their machine learning applications. Microsoft is huge in the PyTorch game. It's absolutely everywhere. So if that's not enough reason to use PyTorch, well then maybe you're in the wrong course. So you've seen enough reasons of why to use PyTorch. I'm going to give you one more. That is that it helps you run your code, your machine learning code, accelerated on a GPU. We've covered this briefly, but what is a GPU / a TPU? Because this is more of a newer chip these days. A GPU is a graphics processing unit, which is essentially very fast at crunching numbers. Originally designed for video games. If you've ever designed or played a video game, you know that the graphics are quite intense, especially these days. And so to render those graphics, you need to do a lot of numerical calculations. And so the beautiful thing about pytorch is that it enables you to leverage a GPU through an interface called CUDA, which is, there's a lot of words I'm going to throw at you here, a lot of acronyms in the deep learning space. CUDA. Let's just search CUDA. CUDA Toolkit. So CUDA is a parallel computing platform and application programming interface, which is an API, that allows software to use certain types of graphics processing units for general purpose computing. That's what we want. So pytorch leverages CUDA to enable you to run your machine learning code on NVIDIA GPUs. Now, there is also an ability to run your pytorch code on GPUs, which is a tensor processing unit. However, GPUs are far more popular when running various types of pytorch code, so we're going to focus on running our pytorch code on the GPU. And to just give you a quick example, pytorch on TPU, let's see that. Getting started with pytorch on cloud TPUs, there's plenty of guides for that, but as I said, GPUs are going to be far more common in practice, so that's what we're going to focus on. And with that said, we've said tensor processing unit. Now, the reason why these are called tensor processing units is because machine learning and deep learning deals a lot with tensors. And so, in the next video, let's answer the question, what is a tensor? But before I go through and answer that from my perspective, I'd like you to research this question. So open up Google. Your favorite search engine and type in what is a tensor and see what you find. I'll see you in the next video. Welcome back. In the last video, I left you on the cliffhanger question of what is a tensor, and I also issued you the challenge to research what is a tensor. Because, as I said, this course isn't all about telling you exactly what things are. It's more so sparking a curiosity in you so that you can stumble upon the answers to these things yourself. But let's have a look. What is a tensor? Now, if you remember this graphic, there's a lot going on here. But this is our neural network. We have some kind of input, some kind of numerical encoding. Now, we start with this data. In our case, it's unstructured data because we have some images here, some text here, and some audio file here. Now, these necessarily don't go in all at the same time. This image could just focus on a neural network specifically for images. This text could focus on a neural network specifically for text. And this soundbite or speech could focus on a neural network specifically for speech. However, the field is sort of also moving towards building neural networks that are capable of handling all three types of inputs. For now, we're going to start small and then build up. The algorithms that we're going to focus on are neural networks that focus on one type of data. But the premise is still the same. You have some kind of input. You have to numerically encode it in some form, pass it to a neural network to learn representations or patterns within that numerical encoding, output some form of representation, and then we can convert that representation into things that humans understand. And you might have already seen these, and I might have already referenced the fact that these are tensors. So when the question comes up, what are tensors? A tensor could be almost anything. It could be almost any representation of numbers. We're going to get very hands-on with tensors, and that's actually the fundamental building block of pytorch, aside from neural network components, is the torch.tensor. We're going to see that very shortly, but this is a very important takeaway, is that you have some sort of input data, you're going to numerically encode that data, turn it into a tensor of some kind. Whatever that kind is will depend on the problem you're working with. Then you're going to pass it to a neural network, which will perform mathematical operations on that tensor. Now, a lot of those mathematical operations are taken care of by pytorch behind the scenes. So we'll be writing code to execute some kind of mathematical operations on these tensors. And then the neural network that we create, or the one that's already been created but we just use for our problem, will output another tensor similar to the input but has been manipulated in a certain way that we've sort of programmed it to. And then we can take this output tensor and change it into something that a human can understand. So to remove a lot of the text around it, make it a bit more clearer, if we were focusing on building an image classification model, so we wanted to classify whether this was a photo of ramen or spaghetti, we would have images as input. We would turn those images into numbers, which are represented by a tensor. We would pass that tensor of numbers to a neural network, or there might be lots of tensors here. We might have 10,000 images, we might have 1 million images, or in some cases, if you're Google or Facebook, you might be working with 300 million or 1 billion images at a time. The principle still stands that you encode your data in some form of numerical representation, which is a tensor, pass that tensor, or lots of tensors, to a neural network. The neural network performs mathematical operations on those tensors, outputs a tensor, we convert that tensor into something that we can understand as humans. And so with that being said, we've covered a lot of the fundamentals. What is machine learning? What is deep learning? What is neural network? Well, we've touched the surface of these things. You can get as deep as you like. We've covered why use PyTorch. What is PyTorch? Now, the fundamental building block of deep learning is tensors. We've covered that. Let's get a bit more specific in the next video of what we're going to cover code-wise in this first module. Oh, I'm so excited. We're going to start code soon. I'll see you in the next video. Now it's time to get specific about what we're going to cover code-wise in this fundamentals module. But I just want to reiterate the fact that going back to the last video where I challenged you to look up what is a tensor, here's exactly what I would do. I would come to Google, I would type in the question, what is a tensor? There we go. What is a tensor in PyTorch? It knows, Google knows that using that deep learning data that we want to know what a tensor is in PyTorch. But a tensor is a very general thing. It's not associated with just PyTorch. Now we've got tensor on Wikipedia, we've got tensor. This is probably my favorite video on what is a tensor by Dan Fleisch. Fleisch, I'm probably saying that wrong, but good first name. And this is going to be your extra curriculum for this video and the previous videos to watch this on what is a tensor. And now you might be saying, well, what gives? I've come to this course to learn PyTorch, and all this guy's doing, all you're doing, Daniel, is just Googling things when a question comes up. Why don't you just tell me what it is? Well, if I was to tell you everything about deep learning and machine learning and PyTorch and what it is and what it's not, that course would be far too long. I'm doing this on purpose. I'm searching questions like this on purpose because that's exactly what I do day to day as a machine learning engineer. I write code like we're about to do, and then if I don't know something, I literally go to whatever search engine I'm using, Google most of the time, and type in whatever error I'm getting, or PyTorch, what is a tensor, something like that. So I want to not only tell you that it's okay to search questions like that, but it's encouraged. So just keep that in mind as we go through the whole course. You're going to see me do it lots. But let's get into what we're going to cover. Here we go. Now, this tweet is from Elon Musk. And so I've decided, you know what, let's base the whole course on this tweet. We have learning ML DL from university. You have a little bit of a small brain. Online courses, well, like this one, that brain's starting to explode and you get some little fireworks. From YouTube, oh, if you're watching this on YouTube, look at that, shiny brain. From articles, my goodness. Lucky that this course comes in article format. If you go to learnpytorch.io, all of the course materials are in online book format. So we're going to get into this fundamentals section very shortly, but if you want a reference, the course materials are built off this book, and by the time you watch this, there's going to be more chapters here. So we're covering all the bases here, and then finally, from memes, you would ascend to some godlike creature, I think that's hovering underwater. So that is the best way to learn machine learning. So this is what we're going to start with, ML, DL from university, online courses, YouTube from articles, from memes. No. But kind of, yeah. Here's what we're going to cover, broadly. So now, in this module, we are going to cover the PyTorch basics and fundamentals, mainly dealing with tensors and tensor operations. Remember, a neural network is all about input tensors, performing operations on those tensors, creating output operations. Later, we're going to be focused on pre-processing data, getting it into tensors, so turning data from raw form, images, whatever, into a numerical encoding, which is a tensor. Then we're going to look at building and using pre-trained deep learning models, specifically neural networks. We're going to fit our model to the data, so we're going to show our model or write code for our model to learn patterns in the data that we've pre-processed. We're going to see how we can make predictions with a model, because that's what deep learning and machine learning is all about, right? Using patterns from the past to predict the future. And then we're going to evaluate our model's predictions. We're going to learn how to save and load our models. For example, if you wanted to export your model from where we're working to an application or something like that. And then finally, we're going to see how we can use a trained model to make predictions on our own data, on custom data, which is very fun. And how? Well, you can see that the scientist has faded out a little bit, but that's not really that true. We're going to do it like cooks, not chemists. So chemists are quite precise. Everything has to be exactly how it is. But cooks are more like, oh, you know what? Add a little bit of salt, add a little bit of butter. Does it taste good? Okay, well then we're on. But machine learning is a little bit of both. It's a little bit of science, a little bit of art. That's how we're going to do it. But I like the idea of this being a machine learning cooking show. So welcome to Cooking with Machine Learning, Cooking with PyTorch with Daniel. And finally, we've got a workflow here, which, ta-da! We have a PyTorch workflow, which is one of many. We're going to kind of use this throughout the entire course. Is step 1, we're going to get our data ready. Step 2, we're going to build or pick a pre-trained model to suit whatever problem we're working on. Step 2.1, pick a loss function and optimizer. Don't worry about what they are, we're going to cover them soon. Step 2.2, build a training loop. Now this is kind of all part of the parcel of step 2, hence why we've got 2.1 and 2.2. You'll see what that means later on. Number 3, we're going to fit the model to the data and make a prediction. So say we're working on image classification for ramen or spaghetti. How do we build a neural network or put our images through that neural network to get some sort of idea of what's in an image? We'll see how to do that. We'll evaluate our model to see if it's predicting BS or it's actually going all right. And number 5, we're going to improve through experimentation. That's another big thing that you'll notice throughout machine learning, throughout this course, is that it's very experimental. Part art, part science. Number 6, save and reload your trained model. Again, I put these with numerical order, but they can kind of be mix and match depending on where you are in the journey. But numerical order is just easy to understand for now. Now, we've got one more video, maybe another one, before we get into code. But in the next video, I'm going to cover some very, very important points on how you should approach this course. I'll see you there. I would recommend approaching this course. So I'm a machine learning engineer on purely writing code. I will be linking extracurricular resources for you to learn more about what's going on behind the scenes of the code. My idea of teaching is that if we can code together, write some code, see how it's working, that's going to spark your curiosity to figure out what's going on behind the scenes. So motto number 1 is, if in doubt, run the code. Write it, run the code, see what happens. Number 2, I love that. Explore and experiment. Again, approach this with the idea, the mind of a scientist and a chef, or science and art. Experiment, experiment, experiment. Try things with rigor like a scientist would, and then just try things for the fun of it like a chef would. Number 3, visualize what you don't understand. I can't emphasize this one enough. We have 3 mottos so far. If in doubt, run the code. You're going to hear me say this a lot. Experiment, experiment, experiment. And number 3, visualize, visualize, visualize. Why is this? Well, because we've spoken about machine learning and deep learning deals with a lot of data, a lot of numbers. And so I find it that if I visualize some numbers in whatever form, that isn't just numbers all over a page, I tend to understand it better. And there are some great extra resources that I'm going to link that also turn what we're doing, so writing code, into fantastic visualizations. Number 4, Ask questions, including the dumb questions. Really, there's no such thing as a dumb question. Everyone is just on a different part of their learning journey. And in fact, if you do have a quote-unquote dumb question, it turns out that a lot of people probably have that one as well. So be sure to ask questions. I'm going to link a resource in a minute of where you can ask those questions. But please, please, please ask questions not only to the community, but to Google, to the internet, to wherever you can, or just yourself. Ask questions of the code and write code to figure out the answer to those questions. Number 5, do the exercises. There are some great exercises that I've created for each of the modules. If we go, have we got the book version of the course up here? We do. Within all of these chapters here, down the bottom is going to be exercises and extra curriculum. So we've got some exercises there. I'm not going to jump into them, but I would highly recommend, don't just follow along with the course and code after I code. Please, please, please give the exercises a go, because that's going to stretch your knowledge. We're going to have a lot of practice writing code together, doing all of this stuff here, but then the exercises are going to give you a chance to practice what you've learned. And then, of course, extra curriculum, well, hey, if you want to learn more, there's plenty of opportunities to do so there. And then finally, number 6, share your work. I can't emphasize enough how much writing about learning deep learning or sharing my work through GitHub or different code resources or with the community has helped with my learning. So if you learn something cool about PyTorch, I'd love to see it. Link it to me somehow in the Discord chat or on GitHub or whatever. There'll be links of where you can find me. I'd love to see it. Please do share your work. It's a great way to not only learn something, because when you share it, when you write about it, it's like, how would someone else understand it? But it's also a great way to help others learn too. And so we said how to approach this course. Now let's go how not to approach this course. I would love for you to avoid overthinking the process. So this is your brain on fire. So avoid having your brain on fire. That's not a good place to be. We are working with PyTorch, so it's going to be quite hot, just playing on words with times, and then I've practiced. It doesn't really make. Finally, we've got one more video that I'm going to some fundamental resources that I would like you to be. There is the GitHub repo. So if we click this link, I've got it pinned on my browser, so you might want to do the same while you're going through the course. But this is Mr. Debug. So my GitHub/PyTorch Deep Learning. It is still a work in progress at the time of recording this video, but by the time you go through it, it won't look too much different, but there'll just be more materials. You'll have materials outline, section, what does it cover? As you can see, some more are coming soon at the time of recording this, so these will probably be done by the time you watch this. Exercise and extra curriculum, there'll be links here. Basically, everything you need for the course will be in the GitHub repo. And then if we come back, also on the GitHub repo, the same repo, so Mr. Debug/PyTorch Deep Learning, if you click on discussions, this is going to be the Q&A. This is just the same link here. The Q&A for the course. So if you have a question here, you can click new discussion, you can go Q&A, and then type in video, and then the title, PyTorch, fundamentals, and then go in here, or you could type in your error as well. What is ndim for a tensor? And then in here, you can type in some stuff here. Hello, you can click new discussion. Also on the GitHub repo, the same repo. So Mr. Debug/PyTorch Deep Learning. If you click on discussions, this is going to be the Q&A. This is just the same link here. The Q&A for the course. So if you have a question here, you can click new discussion. You can go Q&A, and then type in video, and then the title, PyTorch, fundamentals, and then go in here, or you could type in your error as well. What is ndim for a tensor? And then in here, you can type in some stuff here. Hello, I'm having trouble on video XYZ. Put in the name of the video so that way I can, or someone else can help you out. And then code, you can go 3 backticks, write Python, and then you can go import torch.randan, which is going to create a tensor. We're going to see this in a second. Yeah. And then if you post that question, the formatting of the code is very helpful that we can understand what's going on and what's going on here. So this is basically the outline of how I would ask a question. Video, this is going on. What is such and such for whatever's going on? Hello, this is what I'm having trouble with. Here's the code and here's what's happening. You could even include the error message, and then you can just click start discussion, and then someone, either myself or someone else from the course, will be able to help out there. And the beautiful thing about this is that it's all in one place. You can start to search it. There's nothing here yet because the course isn't out yet, but as you go through it, there'll probably be more and more stuff here. Then if you have any issues with the code that you think needs fixed, you can also open a new issue there. I'll let you read more into what's going on. I've just got some issues here already about the fact that I need to record videos for the course. I need to create some stuff, but if you think there's something that could be improved, make an issue. If you have a question about the course, ask a discussion. And then if we come back to the keynote, we have one more resource. So that was the course materials, all live in the GitHub. The course Q&A is on the course GitHub's discussions tab, and then the course online book. Now, this is a work of art. This is quite beautiful. It is some code to automatically turn all of the materials from the GitHub. So if we come into here, code, if we click on notebook 00, this is going to, sometimes if you've ever worked with Jupyter notebooks on GitHub, they can take a while to load. So all of the materials here automatically get converted into this book. So the beautiful thing about the book is that it's got different headings here. It's all readable, it's all online, it's going to have all the images there, and you can also search some stuff here. PyTorch training steps. Creating a training loop in PyTorch. Beautiful. We're going to see this later on. So they're the 3 big materials that you need to be aware of, the 3 big resources for this specific course. Materials on GitHub, course Q&A, course online book, which is learnpytorch.io. Simple URL to remember. All the materials will be there. And then specifically for PyTorch, all things PyTorch. The PyTorch website and the PyTorch forums. So if you have a question that's not course related but more PyTorch related, I'd highly recommend you go to the PyTorch forums, which is available at discuss.pytorch.org. We've got a link there. Then the PyTorch website, pytorch.org. This is going to be your home ground for everything PyTorch, of course. We have the documentation here. And as I said, this course is not a replacement for getting familiar with the PyTorch documentation. The course actually is built off all of the PyTorch documentation. It's just organized in a slightly different way. So there's plenty of amazing resources here on everything to do with PyTorch. This is your home ground. And you're going to see me referring to this a lot throughout the course. So just keep these in mind. Course materials on GitHub, course discussions, learnpytorch.io. This is all for the course. And all things PyTorch specific, so not necessarily this course, but just PyTorch in general, the PyTorch website and the PyTorch forums. With that all being said, we've come so far. We've covered a lot already, but guess what time it is? Let's write some code. I'll see you in the next video. We've covered enough of the fundamentals so far. Well, from a theory point of view, let's get into coding. So I'm going to go over to Google Chrome. I'm going to introduce you to the tool, one of the main tools we're going to be using for the entire course, and that is Google Colab. So the way I would suggest following along with this course is, remember, one of the major ones is to code along. So we're going to go to colab.research.google. I've got a typo here. Classic. You're going to see me do lots of typos throughout this course. colab.research.google.com. This is going to load up Google Colab. Now, you can follow along with what I'm going to do, but if you'd like to find out how to use Google Colab from a top-down perspective, you can go through some of these. I'd probably recommend going through overview of collaboratory features. But essentially, what Google Colab is going to enable us to do is create a new notebook. And this is how we're going to practice writing PyTorch code. So if you refer to the reference document of learnpytorch.io, these are actually Colab notebooks just in book format, so online book format. So these are the basis materials for what the course is going to be. There's going to be more here, but every new module, we're going to start a new notebook, and I'm going to just zoom in here. So this one, the first module is going to be 00 because Python code starts at 00, and we're going to call this PyTorch Fundamentals. I'm going to call mine video, just so we know that this is the notebook that I wrote through the video. And what this is going to do is if we click connect, it's going to give us a space to write Python code. So here we can go print, hello, I'm excited to learn PyTorch. And then if we hit shift and enter, it comes out like that. But another beautiful benefit of Google Colab, PS, I'm using the pro version, which costs about $10 a month or so. That price may be different depending on where you're from. The reason I'm doing that is because I use Colab all the time. However, you do not have to use the paid version for this course. Google Colab comes with a free version, which you'll be able to use to complete this course. If you see it worthwhile, I find the pro version is worthwhile. Another benefit of Google Colab is if we go here, we can go to runtime. Let me just show you that again. Runtime, change runtime type, hardware accelerator, and we can choose to run our code on an accelerator here. Now we've got GPU and TPU. We're going to be focused on using GPU. If you'd like to look into TPU, I'll leave that to you. But we can click GPU, click save, and now our code, if we write it in such a way, will run on the GPU. Now we're going to see this later on. Code that runs on the GPU is a lot faster in terms of compute time, especially for deep learning. So if we write here, NVIDIA SMI, we now have access to a GPU. In my case, I have a Tesla P100. It's quite a good GPU. You tend to get the better GPUs if you pay for Google Colab. If you don't pay for it, you get the free version, you get a free GPU. It just won't be as fast as the GPUs you typically get with the paid version. So just keep that in mind. Whole bunch of stuff that we can do here. I'm not going to go through it all because there's too much, but we've covered basically what we need to cover. So if we just come up here, I'm going to write a text cell. So oo.pytorch fundamentals. And I'm going to link in here, resource notebook. Now you can come to learnpytorch.io and all the notebooks are going to be in sync. So 00.
Okay, so it's a full the US video computer being the NVIDIA GPU. Cool. So everything's working nicely. If you want to poke around with the terminal, by the way, you can just do plus. If you want to poke around with the terminal, by the way, you can just do plus and do new terminal. If you type NVIDIA SMI, now something fun, doing something benefit. So you click generate, it's going to write some code for us. 3x3 matrix. I'm sure all the time is spent. Since I set it to ephemeral, I'll just deprovision it.
We can put this in here. Resource notebook is there. You can come to the course GitHub, and then we go back. This is where you can see what's going on. This is PyTorch Deep Learning projects, as you can see what's happening. At the moment, I've got PyTorch course creation because I'm in the middle of creating it. But if you have a question, you can come to mrdebug/PyTorch Deep Learning/discussions, which is this tab here, and then ask a question by clicking new discussion. So any discussions related to this notebook, you can ask it there. And I'm going to turn this, right now this is a code cell. Colab is basically comprised of code and text cells. I'm going to turn this into a text cell by pressing Command MM, Shift and Enter. Now we have a text cell, and then if we wanted another code cell, we could go like that, text, code, yada, yada, yada. But I'm going to delete this. And to finish off this video, we're going to import PyTorch. So we're going to import torch, and then we're going to print torch ... version. So that's another beautiful thing about Google Colab, is that it comes with PyTorch pre-installed in a lot of other common Python data science packages, such as we could also go import pandas as PD, import numpy as np, import matplotlib.pyplot as plt. This is Google Colab is by far the easiest way to get started with this course. You can run things locally. If you'd like to do that, I'd refer to you to is matplotlib.pyplot as plt. Google Colab is by far the easiest way to get started with this course. You can run things locally. If you'd like to do that, I'd refer to you to PyTorch Deep Learning. There's going to be setup.md. Getting set up to code PyTorch. We've just gone through number 1, setting up with Google Colab. There is also another option for getting started locally. Right now, this document's a work in progress, but it'll be finished by the time you watch this video. This is not a replacement, though, for the PyTorch documentation for getting set up locally. So if you'd like to run locally on your machine rather than on Google Colab, please refer to this documentation or setup.md here. But if you'd like to get started as soon as possible, I'd highly recommend you using Google Colab. In fact, the entire course is going to be able to be run through Google Colab. So let's finish off this video. Make sure we've got PyTorch ready to go. And of course, some fundamental data science packages here. Wonderful. This means that we have PyTorch 1.10.0. So if your version number is far greater than this, maybe you're watching this video a couple of years in the future and PyTorch is up to 2.11, maybe some of the code in this notebook won't work. But 1.10.0 should be more than enough for what we're going to do. And plus CU111, CU111, stands for CUDA version 11.1, I believe. And what that would mean is if we came in here and we wanted to install it on Linux, which is what Colab runs on, there's Mac and Windows as well. We've got CUDA. Yeah, so right now, as of recording this video, the latest PyTorch build is 1.10.2, so you'll need at least PyTorch 1.10 to complete this course, and CUDA 11.3, so that's CUDA Toolkit. If you remember, CUDA Toolkit is NVIDIA's programming, there we go, NVIDIA developer. CUDA is what enables us to run our PyTorch code on NVIDIA GPUs, which we have access to in Google Colab. Beautiful. So we're set up, ready to write code. Let's get started in the next video writing some PyTorch code. This is so exciting. I'll see you there. So we've got set up, we've got access to PyTorch, we've got a Google Colab instance running here, we've got a GPU because we've gone up to runtime, change runtime type, hardware accelerator. You won't necessarily need a GPU for this entire notebook, but I just wanted to show you how to get access to a GPU because we're going to be using them later on. So let's get rid of this. And one last thing, how I'd recommend going through this course is in a split window fashion. So for example, you might have the video where I'm talking right now and writing code on the left side, and then you might have another window over the other side with your own Colab window, and you can go new notebook, call it whatever you want, my notebook, you could call it very similar to what we're writing here. And then if I write code over on this side, on this video, you can't copy it, of course, but you'll write the same code here and then go on and go on and go on. And if you get stuck, of course, you have the reference notebook and you have an opportunity to ask a question here. So with that being said, let's get started. The first thing we're going to have a look at in PyTorch is an introduction to tensors. So tensors are the main building block of deep learning in general, or data. And so you may have watched the video, what is a tensor? For the sake of this course, tensors are a way to represent data, especially multi-dimensional data, numeric data that is. But that numeric data represents something else. So let's go in here, creating tensors. So the first kind of tensor we're going to create is actually called a scalar. I know I'm going to throw a lot of different names of things at you, but it's important that you're aware of such nomenclature. Even though in PyTorch almost everything is referred to as a tensor, there are different kinds of tensors. And just to exemplify the fact that we're using a reference notebook, if we go up here, we can see we have importing PyTorch, we've done that, now we're up to introduction to tensors, we've got creating tensors, and we've got scalar, etc., etc., etc. So this is what we're going to be working through. Let's do it together. So scalar, the way to, oops, what have I done there? The way to create a tensor in PyTorch, we're going to call this scalar equals torch.tensor, and we're going to fill it with the number 7. And then if we press or retype in scalar, what do we get back? 7. Wonderful. And it's got the tensor data type here. So how would we find out about what torch.tensor actually is? Well, let me show you how I would. We go to torch.tensor. There we go. We've got the documentation. So this is possibly the most common class in PyTorch other than one we're going to see later on that you'll use, which is torch.nn. And basically everything in PyTorch works off torch.tensor. And if you'd like to learn more, you can read through here. In fact, I would encourage you to read through this documentation for at least 10 minutes after you finish some videos here. So with that being said, I'm going to link that in here. So PyTorch tensors are created using torch.tensor. And then we've got that link there. Oops, typos galore, Daniel. Come on, you're better than this. No, I'm kidding. There's going to be typos galore through the whole course. Okay, now, what are some attributes of a scalar? So some details about scalars. Let's find out how many dimensions there are. Oh, and by the way, this warning, perfect timing, Google Colab will give you some warnings here. Depending on whether you're using a GPU or not, Now, the reason being is because Google Colab provides GPUs to you and I for free. However, GPUs aren't free for Google to provide. So if we're not using a GPU, we can save some resources, allow someone else to use a GPU by going to none. And of course, we can always switch this back. So I'm going to turn my GPU off so that someone else out there, I'm not using the GPU at the moment, they can use it. So what you're also going to see is if your Google Colab instance ever restarts up here, we're going to have to rerun these cells. So if you stop coding for a while, go have a break, and then come back and you start your notebook again, that's one downside of Google Colab, is that it resets after a few hours. How many hours? I don't know exactly. The reset time is longer if you have the Pro subscription, but because it's a free service and the way Google calculate usage and all that sort of stuff, I can't give a conclusive evidence or conclusive answer on how long until it resets. But just know, if you come back, you might have to rerun some of your cells, and you can do that with Shift and Enter. So a scalar has no dimensions, right? It's just a single number. But then we move on to the next thing. Or actually, if we wanted to get this number out of a tensor type, we can use scalar.item. This is going to give it back as just a regular Python integer. Wonderful. There we got the number 7 back. Get tensor back as Python int. Now, the next thing that we have is a vector. So let's write in here, vector, which again is going to be created with torch.tensor, but you will also hear the word vector used a lot too. Now, what is the deal? Oops, 7.7. Google Colab's autocomplete is a bit funny. It doesn't always do the thing you want it to. So if we see a vector, we've got two numbers here. And then if we wanted to find out what is a vector, so a vector usually has magnitude and direction. So what we're going to see later on is, there we go, magnitude, how far it's going and which way it's going. And then if we plotted it, we've got, a vector equals the magnitude would be the length here, and the direction would be where it's pointing. And, here we go, scalar, vector, matrix, tensor. This is what we're working on as well. So the thing about vectors, how they differ with scalars, is how I just remember them, is rather than magnitude and direction, is a vector typically has more than one number. So if we go vector and dim, how many dimensions does it have? So which way it's going, direction. So what we're going to see later on is, there we go, magnitude has, we've got two numbers here. And then if we wanted to find out what is a vector, so a vector usually has magnitude and direction. So what we're going to see later on is, there we go, magnitude, how far it's going and which way it's going. And then if we plotted it, we've got, a vector equals the magnitude would be the length here, and the direction would be where it's pointing. And, here we go, scalar, vector, matrix, tensor. This is what we're working on as well. So the thing about vectors, how they differ with scalars, is how I just remember them, is rather than magnitude and direction, is a vector typically has more than one number. So if we go vector and dim, how many dimensions does it have? It has one dimension, which is kind of confusing, but when we see tensors with more than one dimension, it'll make sense. And another way that I remember how many dimensions something has is by the number of square brackets. So let's check out something else. Maybe we go vector.shape. Shape is 2. So the difference between dimension, so dimension is like number of square brackets, and when I say, even though there's 2 here, I mean number of pairs of closing square brackets. So there's one pair of closing square brackets here, but the shape of the vector is 2. So we have 2 by 1 elements. So that means a total of 2 elements. Now, if we wanted to step things up a notch, let's create a matrix. So this is another term you're going to hear, and you might be wondering why I'm capitalizing matrix. Well, I'll explain that in a second. Matrix equals torch.tensor, and we're going to put 2 square brackets here. You might be thinking, what could the 2 square brackets mean? Or actually, that's a little bit of a challenge. If one pair of square brackets had an ndim of 1, what will the ndim be? Number of dimensions of 2 square brackets. So let's create this matrix. What will the ndim be? Number of dimensions of 2 square brackets. So let's create this matrix. Beautiful. So we've got another tensor here. Again, as I said, these things have different names, like the traditional name of scalar, vector, matrix, but they're all still a torch.tensor. That's a little bit confusing, but the thing you should remember in PyTorch is basically anytime you encode data into numbers, it's of a tensor data type. And so now, how many number of dimensions do you think a matrix has? It has 2. So there we go. We have 2 square brackets. So if we wanted to get matrix, let's index on the 0th axis. Let's see what happens there. So we get 7 and 8. And then we get off the first dimension. 9 and 10. So this is where the square brackets, the pairings come into play. We've got 2 square bracket pairings on the outside here. So we have an ndim of 2. Now if we get the shape of the matrix, what do you think the shape will be? 2 by 2. So we've got 2 numbers here by 2. So we have a total of 4 elements in there. So we're covering a fair bit of ground here, nice and quick, but that's going to be the teaching style of this course, is we're going to get quite hands-on and writing a lot of code and just interacting with it rather than continually going back over and discussing what's going on here. The best way to find out what's happening within a matrix is to write more code that's similar to these matrices here. But let's not stop at matrix. Let's upgrade it to a tensor now. So I might put this in capitals as well. And I haven't explained what the capitals mean yet, but we'll see that in a second. So let's go torch.tensor. And what we're going to do is this time we've done 1 square bracket pairing. We've done 2 square bracket pairings. Let's do 3 square bracket pairings and just get a little bit adventurous, all right? And so you might be thinking at the moment, this is quite tedious. I'm just going to write a bunch of random numbers here. 1, 2, 3, 3, 6, 9, 2, 5, 4. Now, you might be thinking, Daniel, you've said tensors could have millions of numbers. If we had to write them all by hand, that would be quite tedious. And yes, you're completely right. The fact is, though, that most of the time you won't be crafting tensors by hand. PyTorch will do a lot of that behind the scenes. However, it's important to know that these are the fundamental building blocks of the models and the deep learning neural networks that we're going to be building. So, tensor, capitals as well. We have 3 square brackets. So, or 3 square bracket pairings. I'm just going to refer to 3 square brackets at the very start because they're going to be paired down here. How many ndim or number of dimensions do you think our tensor will have? 3, wonderful. And what do you think the shape of our tensor is? We have 3 elements here, we have 3 elements here, 3 elements here, and we have... What do you think the shape of our tensor is? We have 3 elements here, we have 3 elements here, 3 elements here, and we have 1, 2, 3. So maybe our tensor has a shape of 1 by 3 by 3. What does that mean? Well, we've got 3 by 1, 2, 3. That's the second square bracket there. By 1. So that's the first dimension there, or the 0th dimension, because remember PyTorch is 0 indexed. we have, well, let's just, instead of talking about it, let's just get on the 0th axis and see what happens with the 0th dimension. There we go. Okay, so this is the far left one, 0, which is very confusing because we've got a 1 here. But, so we've got, oops, don't mean that. What this is saying is we've got one 3 by 3 shaped tensor. So very outer bracket matches up with this number 1 here. And then this 3 matches up with the next one here, which is 1, 2, 3. And then this 3 matches up with this one, 1, 2, 3. Now, if you'd like to see this with a pretty picture, we can see it here. So dim 0 lines up. So the blue bracket, the very outer one, lines up with the 1. Then dim equals 1, this one here, the middle bracket, lines up with the middle dimension here. And then dim equals 2, the very inner, lines up with these 3 here. So again, this is going to take a lot of practice. It's taken me a lot of practice to understand the dimensions of tensors, but to practice, I would like you to write out your own tensor of, you can put however many square brackets you want, and then just interact with the ndim, shape, and indexing, just as I've done here, but you can put any combination of numbers inside this tensor. That's a little bit of practice before the next video. So give that a shot, and then we'll move on to the next topic. I'll see you there. Welcome back. In the last video, we covered the basic building blocks of data representation in deep learning, which is the tensor, or in PyTorch, specifically torch.tensor. But within that, we had a look at what a scalar is, we had a look at what a vector is, we had a look at a matrix, we had a look at what a tensor is. And I issued you the challenge to get as creative as you like with creating your own tensor. So I hope you gave that a shot, because as you'll see throughout the course and your deep learning journey, a tensor can represent or can be of almost any shape and size and have almost any combination of numbers within it. And so this is very important to be able to interact with different tensors, to be able to understand what the different names of things are. So when you hear matrix, you go, oh, maybe that's a 2-dimensional tensor. When you hear a vector, maybe that's a 1-dimensional tensor. When you hear a tensor, that could be any amount of dimensions. And just for reference for that, if we come back to the course reference, we've got a scalar. What is it? A single number of dimensions, 0. We've got a vector, a number with direction, number of dimensions, 1. A matrix, a tensor. And now here's another little tidbit of the nomenclature of things, the naming of things. Typically, you'll see a variable name for a scalar or a vector as a lowercase. So a vector, you might have a lowercase y storing that data. But for a matrix or a tensor, you'll often see an uppercase letter or variable in Python in our case, because we're writing code. And so I'm not exactly sure why this is, but this is just what you're going to see in machine learning and deep learning code and research papers across the board. This is a typical nomenclature. Scalars and vectors, lowercase, matrix and tensors, uppercase. That's where that naming comes from. And that's why I've given the tensor uppercase here. Now, with that being said, let's jump in to another very important concept with tensors, and that is random tensors. Why random tensors? I'm just writing this in a code cell now. I could go here. This is a comment in Python. Random tensors, but we'll get rid of that. We could just start another text cell here, and then 3 hashes is going to give us a heading. Random tensors there. Or I could turn this again into a